Hi guys, Dr. J here, and in this video I'm going to be going through the derivation for the Kriging equations. Now the basic setup to our problem here is that we've got some data and it's distributed in space. Maybe it's XY space, could be XYZ, could be different types of space variables, but the idea is we have some observations, we have some data, some values, and they're located in space, and we're going to use the spatial information contained in the data to do a good job, or do the best job possible, make use of the most information possible when we're doing interpolation. So the basic idea, the basic equation that we're going to use is Z star is going to be our estimate, or our estimated value at a new location x naught. So x naught here is just a vector which describes the position, so it can be xy, xyz, whatever the position needs to be described by. So we have the estimated value at a new position is going to just be equal to the sum over all of the data. So z without a star is the observed data, so we have that data, at all of the known locations, xi, and we're going to take a weighted average of all those observations. So our new estimate at a new location x naught, our estimated value at that location is going to equal a weighted average of all the existing data where the weights are to be determined. We want to determine what weights we should use to get the best possible estimate. This is the equations, these are called the simple Kriging equations. We'll take this to a more general form next time, but for now, this is the equation that we're going to assume we can use to make our new data estimate. So what we're going to do in the next few steps is solve for the values of lambda that we need in order to minimize the estimation variance. So let me write down the estimation variance. So what I've done here is I've written down here that we want to minimize the estimation variance, which is the expected value of the estimate y star minus y naught, which is the true y, at our new estimation location. That's the difference between the true and the predicted squared, and the expected value of that. That's what we want to minimize. In other words, we want our estimate to be as close as possible to the true value. Now, a couple things to note. I'm using y here instead of z, and y is defined as z. Basically, I'm just defining this in this way so that it's very clear that the value that we're estimating has a mean, the overall field has a mean of 0. So if we take our observations, we need to remove the mean or do something so that all the observations, the residual observations, have a mean of 0. Once we've done that, then we can proceed as follows. So what we're going to do is we're going to take this expectation, we'll expand it out and simplify it just using linearity, and then try to substitute in this definition and see if we can solve for what lambda should be. So let's do the expansion. So what I've done here is I've just used the properties of the expectation operator. I've expanded out this quadratic factor into the full form, and then I've used the fact that expectation is linear and broken up this summation into its individual terms, pulling out the constant 2 here. So now I've sort of broken this up, and now I can substitute in a few things, or I can start to recognize some terms. So the first term that we're going to recognize, there's a different color here. Here we have the expectation of y naught squared. This is the expectation of the observations at the new estimation location. Well, remember, because y has a 0 mean, the mean of y is 0, the variance of y at the new estimation location, the variance of y should be the expected value of y squared, which we have here, minus the mean of y squared. But the mean of y is 0, and so this is actually just sigma naught squared. It's just the variance of y. So this term can just be written as sigma squared naught. It's just the variance of y. Okay, so that's one of our 3 terms. We have the expected value of y star squared. Now, y star is our estimate for y. It's our estimated value that we want to calculate. And so what we need to do is substitute in this summation here and work out what the expected value of that thing is squared. Now I'm going to skip a few of the steps here, but hopefully I'll show enough that will give you guys an idea of how this works. Alright, so I've kind of taken one step in the right direction, so I've got my original expectation of y star squared here. I've substituted in the definition of y star here, just the mathematical formula that we're going to use, and I've got that squared. Now it might be not quite straightforward to see the next step here, but basically you can think about this as just a sum over all the weights and data. So this is now our observed data here. So yi is the observed data at locations xi. I've just sort of abbreviated it. And then we have lambda I, which is the ith weight which goes with each one of the data points. We're going to sum over all those to get our estimate. And so we're going to square these, so you can imagine we're going to end up with lambda i's and lambda j's squared, where the I and the j can be anything from 1 to n. Same thing with the y's. So this is just going to look like a double summation over over I and j 1 to n, lambda I times lambda j, yi times yj. So this is going to end up being a big matrix where we're going to fill in all the values of the matrix with all the different products here. So expectation of this term squared is just equal to the expectation of this double summation term with this product like this. Now the thing to note here is that these lambdas are constants, and expectation can go inside of the summation, and so what we'll end up having is an expected value. I can actually just do this right now. We'll have the double summation is still there, lambda I, lambda j. Again, those are constants. And then we'll have the expected value of yi, expected value of yi times yj here. Now, based on what we did for term number 3 just a moment ago, which I've erased now, but this is expected value of yi times yj. If we just added a minus mu y squared, this would be the covariance of yi with yj. So again, because the mean is 0, this expected value of yi times yj, that's just the covariance of yi with yj. So we can actually replace this term with, I'll call it capital C for covariance, or actually, I'll call it sigma squared ij. Okay, where the idea here is that this is now a number which describes the covariance between xi and xj. I could also write this as, let's say, sigma squared of xi and xj, where the idea here is that this is just one number. It's the covariance between the data at xi and xj. So we just have lambda I, some double summation over I and j, lambda I, lambda j, covariance of I and j. That's our first term. We already know we have a minus 2 here, and then we have that other summation, which we'll come back to in a second. And then we have sigma naught squared, which is just the overall variance. So we've gotten 2 out of 3 terms now, and we can do the last term by comparing to what we've done here for the first term. It was y naught star times y naught, expected value of y naught star times y naught. So the expectation of the estimate times the true value. And now we'll still have this summation term in here, but now we'll be multiplying this by y naught. So instead of being this quantity squared, it'll be this quantity times y naught. And it's pretty easy to see that if we do this rearranging like we did before, this is going to just end up being the sum from I equals 1 to n. Again, summing over all the data points, sum equals I from 1 to n of lambda I times the expectation of yi minus y naught. Now here we've again sort of substituted the data, the summation over all the data points of the weights times the observations. We've substituted that for our estimate. So we've substituted the definition of the estimate, the mathematical definition, which is using the original data points. And again, here I'm using z, that just means the mean is still there. By using y, I'm saying we've remove the mean. And so this now is just like before. We had the covariance of yi with yj. This is now just the covariance of yi with y naught. And actually, before I use sigma squared ij, probably I should have just had sigma ij to denote the covariance between xi and xj. And here we have, I'll just use sigma I naught for the covariance between xi and x naught. So we've got all three of our terms now, and we can put these all together. So now I've written out the whole expression. We have our estimation variance. Here it is again the expectation of the estimate minus the true value squared. We've expanded that out, simplified, substituted in to get a double summation. And again, we're going to minimize this. We're going to minimize this double summation over I and j. Here's the covariance between xi and xj. Minus 2 times the summation over the weights and the covariances between xi and the new observation or estimation location. So the new location where we want to make the prediction. And then we're adding in the variance of the prediction. So just a constant term. We can write this in this way. This is the summation form of the expression. Or we can write it as a matrix vector system. So here I've just rewritten the same thing, but as a matrix vector system, where we have lambda transpose times capital sigma now, where capital sigma is a matrix with all the little individual sigma ij's. Then we have our lambda again. So this quantity will be just a constant, a number. Minus 2 times a dot product between the weights lambda and the sigma I0. I've kept the I0 there. This is a whole vector now, but it's just denoting the fact that this is the covariances between all the data and the estimation location. And then there's our estimation variance again. So all these are now scalars. It's a constant. So this will be sum. This is going to be our expectation, or our estimation variance, I should say. And we want to minimize this. So if we want to minimize something, what do? We take the derivative. In this case, the derivative with respect to the lambdas, because we're solving for what the lambdas ought to be, in order to minimize this variance. And then we'll set that equal to 0. So what does that look like? Well, if we do that, again, if you're not familiar with matrix vector algebra, I'm going to skip some of these details. But what we end up getting, in order to minimize this, we want to minimize this whole quantity. And so in matrix vector notation, again, we're going to get the following system of equations. So what do we have here? Again, I'm using capital sigma to denote the matrix of all the sigma ij's. So this is just the covariance of all the data with itself. Here's our vector of lambdas. That's what we're going to solve for. And then here is our sigma I naughts. So the covariance of all the data with the estimation location. Now let's step back for a second and look at what we've got here. We've used these two constraints to sort of set up what lambda should be. We want to use lambdas in this type of equation to solve for what our new estimate is. And we want to minimize the estimation variance. We can take the derivative of this with respect to lambda, set that equal to 0. You end up with this equation. And so if we solve this equation for the lambdas, so again, this matrix is the covariance of all the data with each other. We know what that is. We know where the data are located, so we can calculate what those covariances are. We know where we want to solve for a new data. So we know where we want to make the prediction for a new value. And so we know what this term is. This is just the covariance with all the data locations with the new estimation location. So this is all about locations in these covariance matrices and vectors. There's no data involved here. Actually, the only thing in these sigmas is the locations of the data. The only part that we need to know, the information that we need to know, is about the locations of the data. And so we can use those things to solve for the weights that minimize the estimation variance, and so we're able to get the best possible, in the least squares sense, the best possible estimate of weights, which we can use to get the best possible estimate of our data that we want to predict. And so using these assumptions about what the solution should look like leads us to the simple Kriging equations, which we can, again, solve this system for the lambdas, plug those back into our equation here, and then get our estimate at the new estimation location based on the data that we already have. A couple of things to note. these weights, right, are going to be a function of distance. So we've accounted for distance between observations. By this term, this is getting the covariance between all of our data points and our new estimation location. We can extrapolate beyond our data. If we extrapolate beyond our data, these covariances go down to 0, and so what we end up with is just an estimate of the mean, which in this case, the mean is 0, so we just end up with an estimate of 0. When we do the more general case where we can solve for an unknown mean, what will happen is, as we get very far away from our data, the Kriging estimate will just go to the mean, and we'll just have an estimate of the mean, or which is the mean. We've accounted for the fact that there are relationships and redundancies in the data itself from this term. So our covariance matrix is telling us how the data are related to each other, or how they are expected to be related to each other, how they're covarying with each other. And so we can account for redundancy in the data, or clustering in the data, through this capital sigma term. So we've done a lot. Kriging has given us a lot. It's given us the minimum, best linear unbiased estimate of our new estimation location based on these assumptions. It's given us a measure which we can use to predict a value at any point, anywhere, either within our set of data or even outside the set of data that we have, extrapolating. It's minimized the variance of the prediction. So Kriging has done a lot. And we can use the Kriging equations to come up with an uncertainty estimate, so we won't only have an estimate for what the predicted value would be, we'll have an estimate of how uncertain that value would be at any given location. And we'll go through that in another video, but for now, thanks for listening, and I'll see you in the next video.